The first talk will be by Jonas, that he will talk to us about journey planning in public transportation networks. Put here.
Thank you. Can you? I think I need to keep it like this. All right. Really? Doesn't sound like it's picking up. It's fine. Okay. Then let's get started. The nice thing about this problem is that it's really easy to motivate journey planning because you've all used this before. In fact, you've probably used it to get here. So I would say that journey planning in public transportation is probably the most widespread application of temporal graphs, period. So despite this, it's not usually framed as a shortest path problem. Not as a temporal graph problem, but as a shortest path problem in general. And one of the things I want to convince you of is that actually temporal reachability is the right way to think about this, not necessarily shortest paths. And then I want to tell you a little bit about how we make these algorithms really, really fast in practice. And afterwards, I want to talk a little bit about how both communities, the journey planning people and the temporal graphs people, can actually learn a bit from each other. Okay, let's define our terms. So a public transit network has a set of stops. So these are bus stations or train stations. And then you have vehicles arriving at specific stations at a specific point in time. So this is what we call an event up there at 8 o'clock. And then it travels to the next stop. This is called a connection. And then if you have a whole chain of these connections, that's called a trip. And then maybe 1 hour later on the same day, you would have another trip going along the same sequence of stops. And so we can group these two into a line. Now, there might be other lines in the network, and we need to be a little bit careful with this term because the way transit agencies use this term is not how we use it. In what a transit agency calls a line, sometimes it might skip one of the stops at some points in time, and then the next trip 1 hour later will take the same, will visit the stop again. For our purposes, this is not a line. These two trips would belong to different lines. Okay, there's also footpaths, but I didn't want to make the talk too complicated, so I'm mostly ignoring those. And now the journey planning problem, or at least the most common version of it, is this. I have a source stop, I have a target stop, and then I have an earliest possible departure time. In this case, it's 10:30. And then I want to get from S to T. And there are several criteria I might want to optimize. First of all, of course, I want to arrive as early as possible, but that's not the only thing I care about. I might also want to minimize the number of trips that I use. You will know this from your own experience. Every time you have to change between trips, first of all, it's cumbersome. And also there's always the risk that you will miss your connection because one of the trips is delayed. I come from Germany, so I have a lot of experience with delayed trips. There might be other criteria that you care about, but for now, let's stick with those two. And because we have competing criteria, we usually compute the Pareto front. And then for every entry in the Pareto front, we will have one representative journey. So let's see how this looks. First of all, I could take the green trip from S to T. It's a direct journey, so I have one trip and I arrive at 12 o'clock. I could also take a later trip of the same line, but then I would just arrive later and not save any trips. So this would not be in the Pareto front. I could also take the yellow line and then switch at this stop down here, take the red line. Now I've used two trips, but I arrive early at 11:30. So this is also an interesting option. And I could also, instead of exiting at this stop, take the yellow line a little bit longer, take this footpath, enter the red line a little bit earlier, and still arrive at 11:30 with two trips. So this is the same cost vector, and because I only want one representative journey for each cost vector, I can get rid of this one too. Okay, usually when we work on these problems, we work on something called the time expanded graph. And this is basically what you would know as the static expansion. I've also heard it referred as the event graph. So for each event in the timetable, we have three nodes. We have an arrival node in yellow. Then we have a departure node in green. And of course, there's an edge going from the arrival node to the departure node to represent staying in the trip. Then from the departure node, you have an edge to the next arrival node, and this is one connection of the trip. And then you have these transfer nodes in the middle, and this is for changing between trips. So the arrival nodes have edges to the next transfer node that you can catch. From there, you can either enter the next departure node, or there's this chain going from the top to the bottom, downwards in time, if you are waiting at the stop for a later trip. All of these nodes are labeled with their event time. And then to represent the number of trips that you use, we can give costs to these edges. So all of the edges from transfer nodes to departure nodes will have cost 1 to represent that we've now entered an additional trip, and all the other ones have cost 0. This graph has size O of m, where m is the number of connections. And with that, let's start with a little warm-up. So instead of focusing on the Pareto problem, let's first solve only for arrival time. So this is the earliest arrival path problem. In the early public transit literature, until about the 2010s, people would just apply Dijkstra's algorithm to the time-expanded graph. I mean, this works and it's reasonably fast, but it doesn't exploit the temporal structure of the graph at all. So if you look into the temporal graph literature, it will tell you that you can exploit the fact that the time-expanded graph is a DAG, and you have a really simple dynamic program where you just sort all of the temporal edges in ascending order of time. You sweep over all of them, and this solves the problem in linear time. And there's a paper from 2014 that would tell you this. And it turns out that exactly the same algorithm is known in the public transit community as the connection scan algorithm, and it was actually published 1 year earlier. So this is a case where both communities arrived at the same result at pretty much the same time without knowing about each other. There's actually a different way that we can do this in linear time, and that's a bit closer to what we will be using later on. So if I have the time-expanded graph, I can pick out the earliest transfer node at my source stop with time above my minimum departure time. So we have that down here at S. And then I can look for the earliest reachable transfer node at my target station T. Unfortunately, you can't see this, but down here to the right, this is the target station T. Actually, can I quickly move this over maybe? Okay. I can minimize it. Okay. Yeah. So here you see the station T. And down there, the first one is actually the earliest reachable one. So I can just do a breadth first search to find this in linear time. Okay, and now I need to go back there. Now, instead of minimizing arrival time, let's minimize the number of trips without caring about the arrival time at all. This would be a min-cost temporal path, where the costs are the 0, 1 costs that represent the number of trips that I take. And because all of the costs are 0 or 1, I can run Dijkstra's algorithm with a priority queue that's bucket-based. So for each cost value that I encounter, I have one bucket that's just a FIFO queue. And then I process the whole bucket before I move on to the next one. And that actually gives me linear time as well. I can view this in a slightly different way. Let's say that K is an upper bound on the number of trips that I will encounter in any journey. In the worst case, this may be M, but in practice, it's usually fairly small, so it might be 8 or 10 or something like that. So now I can take my time-expanded graph and I can create K copies of it, and we will call these layers. So you see down here, I start out with layer 0, the blue stuff down there, and then every time I have an edge of cost 1, and these are the ones from the transfer nodes to the departure nodes, they go to the next layer. So I have layer 1 in yellow down here. And now if you look at these edges that go upwards, these don't go to the departure nodes on the same layer, they go to the one on the next layer. So I have layer 2 up here, and I would have layer 3 up there, but I didn't draw that. So I have all of these layers. And now if I think about what the bucket version of Dijkstra's algorithm does, it's actually pretty much a BFS that goes layer by layer. So at first, I would explore all of layer 1, and because it's a FIFO queue, it's just a BFS, and then once I've done all of that, I would move on to the next layer. So I should really think about this more as a version of BFS. And now, in this case, in layer 1, I have a node down there. It's the middle one it's the first one I can reach. And in layer 2, I can actually reach an earlier one. So that would be my solution. Runtime of this is O of km. And if k is small enough, we can think of this as linear time. Now, the nice thing about this is when now I go back to my Pareto problem, I can use the same algorithm. I can still do my layer BFS. I just need to be more careful about what my result will be, because actually now I want to find the earliest reachable transfer node at T in each layer. So in layer 1, this is the earliest arrival time I can achieve with using just one trip. And then in layer 2, I might have an even earlier one and so forth. So I have one node at most per layer that I care about, and I can still do this in time O of km. Okay. Now, this is actually fairly close already to what we do in practice, but there are a couple of extra tricks. So let me introduce you to the trip-based routing algorithm. The first trick is about all of those transfer nodes. You have this chain of transfer nodes at every station, and going through all of those is quite time-consuming, and we can shortcut these edges. So there's a pre-computation algorithm that's quite fast that can connect arrival nodes to departure nodes at the same stop, but only if there's actually an optimal path where you would actually do this. So in this case, from the second one to the one at the bottom, there might be an edge, and from the third one too. But from the first one, you see there isn't any outgoing edge, and that's because the pre-computation algorithm has figured out that you would never actually transfer from there to anywhere else at the same station in an optimal path. So once I've done that, I can get rid of this whole chain, and I'm just left with this. And now when I answer my query, I never have to look at transfer nodes except at the beginning of the query, and after that I just go through these transfer shortcuts to go from trip to trip. And I can do this with my layer BFS, but I can actually make it a little bit faster in practice with an extra trick, and that is that I treat each trip as a single node, and I scan it in bulk. So let's make a little example. I have two trips down here, and they belong to the same line, and the bottom one comes earlier than the one on the top. And I maintain something called a reached index, which is just a number for each trip that tells me what is the earliest event at that trip that I have reached so far. So let's say I explore this edge, this incoming edge here at the bottom. Then I would scan the rest of the trip, which in this case is just the next event. I would relax all of the outgoing edges, and I now set my reach index to 4 because I have reached the fourth event of this trip. And actually, with the trip that comes later, I can also set it to 4 because if I have reached this event here at the bottom, I would never need to use the one of the trip that comes afterwards, and that's just later than the other one. There's no reason to ever do that. It won't improve any solution. So I also set this to 4. And now the next time I look at this trip, I will not scan the dashed parts anymore. So let's say next I take this edge. Now I will scan the leftover part of the trip at the top, and I will relax the two outgoing edges at the next event, but not the one afterwards. And I now set the index to 3. But with the earlier trip, it's not set to 3 yet, so if I ever reach that part of the trip, I will scan it, because it might improve my solution. And now finally, if I have an edge to the first event here, then I would scan all of these events up to the dashed part at once, relax all of the outgoing edges. And the reason I do this is that because it's much more cache efficient than what a BFS would do. In a BFS where I have a FIFO queue, I would constantly jump around between different trips. And each time I would have to load the data for this trip into memory. This would probably produce a cache miss. It would be quite slow. If I scan the whole subsegment of the trip at once, then I load everything into memory, and now I scan it all in bulk, and that produces much fewer cache misses. So it's faster in practice. And now, of course, I've set my reached index to 1, and I will never look at this trip again. Okay. I promised to tell you about how we make these things really, really fast in practice, and the way that we do that is with indexing. So we pre-compute some amount of auxiliary information about the network, and then we use that for pruning when we're answering a query. So one common ingredient in these indexing algorithms is what I would call edge annotations. So I have some annotations on these edges, and these tell me if I have some additional information about my query, like where is my source located, where's my target located, then for this case, I will have pre-computed some information about whether I need to look at this edge or not. So one example would be goal direction. I could divide my network into regions. And now if I know that my target is in some region X, then I can pre-compute for region X for each edge. Do I need to use this edge if I'm ever going to region X or not? Another thing I could do is hierarchical. So if I know that my edge is far away from both the source and the target, then I would probably not need to look at all of the edges. For example, if I'm going from here to, I don't know, Berlin, I would probably not be looking at local buses in Frankfurt. So there's a lot of edges that I don't need to look at if I'm far away from my source and my target. So these kind of indexing techniques have been applied very successfully to road networks. And in fact, if you use Google Maps today, then the algorithms that they use will use one of these indexing techniques. For public transit, unfortunately, not so much so far. They have not been as successful. And I will tell you about one of the problems because it's related specifically to temporal graphs. These indexing techniques rely on what I call the subpath property. So if I have a shortest path and then I take any subpath of it, it will also be a shortest path. This is true in normal graphs. And this is nice because now if I have pruning information about all of the subpaths, I can glue it together and get information about the path that is made up of these. But as you probably know, the subpath property does not hold in temporal graphs, especially if I'm looking at earliest arrival. So here I'm arriving at 5:50, and then I can either take the red trip or the blue trip. And in both cases, I can switch to the green trip, arrive at the same time. Now, the upper path, if I look at the subpath that starts at the next to last vertex, that one is the shortest path or an earliest arrival path, but the one at the bottom is not. And in fact, because I have a lot of waiting time before I move on to the 8 o'clock trip, I can do a lot of silly things in the meantime. I could even take a round trip that goes for a whole hour, comes back before 8 o'clock, and then enter the trip again. And this would also be an optimal path. And these indexing techniques run into trouble with this situation because it's hard to tell which of these paths should I actually flag as necessary and which of these should I discard. In this case, it seems easy enough. I would just take the upper one, but you can run into situations where it's hard to decide which one to use. And all previous attempts to do indexing either had to sacrifice optimality. So they basically just pretended as that the subpath property holds, even though it does not. And then there will be some query that it will not answer correctly because the gluing together doesn't work. Or they decided to mark more paths than necessary as optimal, and that weakened the pruning. So the pruning effect wasn't as strong, the algorithm wasn't as fast as it could have been. We revisited this for trip-based routing, and we managed to restore the subpath property. We basically said for each entry in the Pareto front, we can choose one canonical representative path, such that every subpath of it is itself canonical. And I mean, in this case, it would just be the upper one. And then we had to modify the search algorithm such that it could actually find this canonical path. And this worked out in our case, but it's not obvious that this is possible. And in fact, there are situations where we could show that it's not possible. And as for the indexing, we found that the best thing to do is to annotate only the transfer shortcuts that trip-based routing produces anyway, because they offer a stronger pruning effect than all the other edges. So if I look at one of those shortcuts, I don't have a laser pointer, right? but let's try with the mouse. So if I have this shortcut down here, if this is necessary for my query, then I also know that this edge and this edge will also be necessary, but not vice versa. If I had only annotated these edges, I would not necessarily know that this shortcut between them is necessary. So annotating only the transfer shortcuts actually gives me all the information that I need. Okay, we turned this into two algorithms. One of them uses goal direction. It's called flash TB. The query times are extremely fast. So on the network of Germany, I can get down to about 0.1 milliseconds. Uses quite a bit of space to do that, 18.8 gigabytes, but I can get it down. I can keep it at less than a millisecond with less than a gigabyte of space. The problem is that the pre-computation effort is quite heavy. On Germany, it takes 30 hours already, and because the effort is quadratic, it does not scale to larger networks. So the second algorithm uses hierarchical pruning. It's called T-Rex. Also has very fast queries, not quite as fast. So on the network of Europe, we're at less than 10 milliseconds if we use quite a lot of space, below 20 if we use a little bit less. And of course, this network is much larger than the Germany network. And the nice thing is that the pre-processing is much faster. It's only about 2 minutes, and it can even support real-time updates. So if I'm told at some point that one of my trips is delayed or canceled, I can incorporate this into the index in a matter of seconds. Okay. To sum up, I hope I have convinced you that public transit journey planning is actually more about temporal reachability than classic shortest paths. And the way that we make this fast in practice is by turning everything into a cache-friendly dynamic program. And we are only just starting to get the hang of how we can do indexing. And to do this, we actually needed some insight that are specific to temporal graphs. And finally, I want to stress again that I think the temporal graphs community and the journey planning community seem to be quite independent so far. I showed you one example where they came up with the same insight independently at the same time. This has happened a lot, and I think this is quite unfortunate. And so my pitch to you is, let's work together more. I think there are a lot of problems that are interesting to both communities where we can probably make progress by looking at it together. So I hope this was interesting to you, and I'm happy to answer any questions that you might have.
Thanks, Jonas, for the talk. Any questions for Jonas?
Hello, nice talk. You said before that for the earliest arrival objective, not necessarily every prefix is itself an earliest arrival.
Yes.
But I might be wrong on this, but I think in the Wu et al. Paper, they said that there exists an earliest arrival path such that every prefix is itself an earliest arrival.
That is true.
You use that.
Yes.
For the data structures?
So we basically use that. It gets a little bit more complicated because we have another objective in there. And then also, I didn't go into this part. There's this pruning. We saw the reach index pruning, right? So there are a lot of equivalent paths that have the same arrival time. And these algorithms make some implicit choices about how to break ties between them. And the tricky part is making this choice of canonical path consistent with all of the choices that the algorithm makes when breaking ties. That's the hard part.
Any other questions for Jonas? I have a quick one. What do you think is what do you think we are missing in order to get significant improvement? Is it algorithmic the problem? Is it data structure? Is it combination? Is it we don't have the hardware? What do you think?
Yeah, so I think there are two answers to this. Actually, if I go back to this. So the problem with the first one, why the preprocessing effort is so large, that's a technical problem. And I think it's solvable. I have some ideas, but it's basically about I need to do a backward search that still finds the same canonical path that a forward search would find, while keeping all of the tie-breaking rules the same. So this is a technical challenge. I think it's solvable. The other reason, if you compare this to road networks, these algorithms are still comparatively slow. And I am not sure if this is because our algorithms are not sophisticated enough, or if it is because these networks have a less hierarchical structure than road networks. That might also be the case. So if you take something like a bus network in a large city, there seems to be no hierarchy at all. Every bus seems to be equally important. So maybe there's not so much that we can do there.
There is one more question.
Hello. Hi, thanks for the talk. Can you go one slide back?
Sure. This one?
One more, sorry. Yeah, this one. I'm a bit confused on the shortest path here. Why can't we just use time difference as the weight in the graph? And then you like the objective then could be, okay, find the shortest path, but with maximize the wait time or like this extra time that we have.
Maximizing the waiting time.
So use the normal shortest path solution. So we can just have, okay, we have two paths here, okay, right?
Yeah.
And then we can find, okay, the time difference 6 to 7. That could be our like the weights of the graphs or like the edges, right? And then we just maximize the extra time that we have, the yellow path that we have.
Yes, I think that would actually work in this case. And I think that's relates to what somebody else says. There is actually a path that always arrives earliest at each subpath. So the challenge is actually not to solve the problem if you only care about earliest arrival. That's doable. And I think the way you said is one way that you could do this. But it gets more complicated when you get into other situations where you might have situations where you have two paths that are both prefix optimal, so they arrive earliest at every prefix, but you still need to make a choice between them. And the situation where these algorithms break down is usually if these choices become inconsistent between different subpaths. So that's probably more the challenge than just solving this.
What if we just use choices? Randomly pick one.
Well, it would have to be consistent globally. So no matter what search I do, it would always have to be the same choice. And actually, with some of these algorithms that we use to do this quickly, the choices are not consistent globally. So part of what we had to do is realize that that's the problem and modify the algorithms so that they do become consistent.